So we are going to be continuing on that particular series on Laplace transform. You remember our Laplace transform, right? It's very simple and technical. I said if you want to take the Laplace transform of a function f of let's say t, right? This function is in t. I'm taking it to the frequency domain. I told you is f of t, right? Exponential minus st, then the t. Now, if you can do this properly, you're going to be getting the function in the frequency domain, right? I told you that this is the Laplace transformation of this particular function. You're taking it from the time domain to the frequency domain, right? Now, this particular exponential minus st, in this case, this is time, but s here is a variable. This variable, actually, s is equal to this variable plus I omega. This particular variable, this should be sigma, then plus I omega. The omega here is a real number, is the real part, why the omega here is the imaginary part. You remember, we were talking about complex numbers, right? We talk about x plus IY. So in engineering, this term, you can clearly see it as this particular Greek alphabet plus J instead of I, then you see omega, which is particular. This now becomes the imaginary part. Now, quickly, I've told you the range must be from 0 to infinity. So we're going to be solving this particular function if f of t is equal to 1, and also if f of t is equal to exponential, the second one, minus at. I have done for f of t when it is equal to exponential at, right? We have done this. So what we are going to be doing today, let me do this quickly. We're going to substitute this function into our Laplace formula over here and solve. So we have integral from 0 to infinity. What am I trying to transform? F of 1, right? So the function here is 1, exponential minus s of t dt. Pardon my voice, this is a live recording and it's for it's an on-demand video, so you can just follow up and learn. Forget about the noise, just concentrate, forget about the background. I'm sorry about that, but this particular video is on demand and is necessary. Now, the function is 1. Obviously, 1 multiplied by anything is still the same thing as 1. So this function can just be exponential minus st dt. Now, remember from integrals, when you integrate exponential function, you're going to get that function back. So I'm going to get this function back, first of all, but I'm going to divide this particular variable. When I differentiate this, the remaining, I'm going to take it as 1 all over what? S. 1 all over S. The variable over here, I'm going to negate it, right? This is the integral of this. But where am I going to evaluate this? I'm going to evaluate this at 2 points. The first point is infinity. The second point is 0. If you're just seeing this video without the previous one, I've actually deliberate and I throw light on what infinity is. It's just a relatively very big number, right? So if I substitute infinity for this, I'm going to have 1 over s, this parameter s, exponential minus s. Instead of t, I'll put infinity, right? Then this is the first part. I'm going to take out when I substitute 0 into it. So I have minus 1 all over s, exponential minus s. Instead of t, I'm going to substitute 0, right? So you see, it's straightforward. I think it's straightforward. So this particular brace, I can make this one the curly brace, right? This is just straightforward. Now, I told you anything attached to infinity goes to 0 because of the exponential sign over there. So this is 0. So we have, this is minus, right? So minus here is going to give us positive 1 all over s. Then here, over here, I'm going to have exponential 0 multiplied by minus s is 0. Now, you remember from indices, anything raised to power 0 is equal to 1. Even x raised to power 0 is equal to 1. Anything raised to power 0 is equal to 1. So here, definitely, we're going to have 1 all over s as the answer. Now, clearly here, you can this condition, s cannot be 0, s cannot be 0. If not, this particular function may not be defined in the time domain or in any other domain, right? Here, s cannot be 0. Then secondly, let me quickly do the second example over here. When we have f of t is equal to exponential minus at. This is very straightforward also. I'm integrating from 0 to infinity. My function here is minus at. I'm going to put back this particular function here. This function is minus at. So I have minus s of t, then I have the t. So this integral, I can put this together since this is multiplication over here. So I have 0 to infinity integral of minus at, which is this one. Then with this one, I'm going to add them together, right? So this is going to be plus, I have another minus s of t, then I have the t. So if I add this together using normal indices, right, I'm going to have exponential. I'm taking out this negative outside here. So I'll be left with at, right, plus st dt. I've taken out negative. Now let me take out t. So I'm integrating this from 0 to infinity. So 0 to infinity, I'm going to take exponential. Minus is now outside. Then I'm going to be left with here a plus s. Then let me put t outside, right? So this is dt. Fantastic. This is accurate. If you do this, you are good to go. You are what? Good to go. Now, good. So here, all I need to do is to differentiate. Similarly, I know if I integrate this guy, I'm going to get that function back. Minus a plus s, right? T, I'm going to get this function back. But here, I'm going to take out, we're going to negate 1 over what? This particular function, which is just at, a plus s. It's the same thing. So this clearly is the same thing as s plus a, because addition is commutative. Integral of minus s plus a, right? This is commutative, but I'm going to be evaluating at 2 points. The first point is infinity, the second point is 0. So let's evaluate at what? Infinity as 0. If I put infinity over here, I'm going to get 1 all over s plus a exponential minus s plus a and infinity. So everything here is going to be 0. So I'm going to have now minus the second part of this equation. So the second part is actually minus this. So we have the second part is minus 1 all over s a, right? So we have s plus a. So we have integral, not integral, exponential minus s plus a, then we have t, right? So this particular part, instead of t now, I'm going to put 0, right? The first one will put infinity over here. The second one, we're going to put 0. So my minus and minus is going to go away. So I have 1 all over s plus a. Then everything here, like I said before, 0 multiplied by everything here is going to be exponential 0. And exponential 0 is actually equal to 1, right? So this is just going to be 1 multiplied by 1. So this particular guy becomes the result of this particular function. How cool is this? This is straightforward. This is what? Amazing. And that is your answer. So stay tuned to this channel. You can share this video with your friends and colleagues. And actually, I'm going to be doing more and more examples. So stay tuned for the next example.